Hi, in this video I'm going to talk about indexing database tables. Indexing is extremely important for computer programmers and database administrators to understand. Luckily, it's really easy to do. Okay, I'm going to come up with a few objectives. I'm going to talk about what an index is. I'm going to show you how to create them on tables, and we'll determine what it is you want to index. So, let's start. Simply put, an index is a way to speed up queries. Now that is a very simplified discussion, but that is the nutshell of an index. It makes your queries run faster. If you remember your big O notation, the complexity of an algorithm, when you do a typical database table search, it is an ON, which means you have to look at every record in the table before you find what you want. So if you're looking at a large database with 20 or 30,000 records in that table, you're going to look at all 20 or 30,000 of them. An index will speed it up dramatically. When you set up an index, the index is O log n. So if you're looking at 10,000 records, that's like 4 records to look at instead of 10,000. So it really speeds up your searches. It does come at a little cost because you now have an additional file on disk and you have a little more disk space taken up, but that speed tends to outweigh the disk space considerations. So indexes will speed up queries. The knee-jerk reaction from beginning programmers is, oh great, let's build an index and everything. No, that's a bad idea. And I'll discuss that later. I want that in your brain right now. You index when you need to, not all the time. Let me demonstrate how indexes are stored on disk. When an index is built, it's going to build a B tree or a balanced tree. And this balanced tree is going to hold pointers to the nodes. So let's take a look at this index. Okay. I'm storing the letters A, B, C, D, E, F, H, J, M, Q, S, T, U, V. I intentionally skipped some letters so I can do some work later on. Here is a simplified balanced tree. You'll have some root node. The root node will be in the middle of these. If you look at this alphabetically, J is greater than everybody to the left and less than everybody to the right. For those of you who took a data structures class, like typical tree. Exactly. Now, the reason they do this is it makes it fast to search. So suppose I'm looking for the letter D. I come in my root node and say, okay, are you D? No, you're not D. So D is less than J, so I come down here to this node, and voila, there it is. Let me turn on my pointer. So are you D? No, you're D. I'm done. So to find my D, I only had to look at 2 records. If I had done this linearly, I'd have had to go A, B, C, D. I'd have had to have 4 looks. So I went from 4 looks to 2. Likewise, if I'm looking for V, are you V? No. Are you V? No. Hey, here's V. I found it in this node. Had I looked for V linearly, I'd have looked at every letter here until I found V. So your indexes are going to be stored on disk in a balanced tree. That disk read does come at a little bit of a hit, but you typically dramatically increase the speed of your searches once you have an index. Now, it's okay if you don't remember how to build a balanced tree. SQL Server does all the work. You're going to write one command and modify the index periodically, but SQL Server does all the work. All right, so we've talked about what's going on behind the scenes. Let's talk about now when you want to build an index. So first off, every time you create a primary key on a table, SQL Server automatically builds you an index. And that's consistent across relational database systems. So MySQL, Oracle does the same thing. Those are called clustered indexes in SQL Server. And I'll talk more about that in a second, but every primary key is automatically an index. You want to build an index on fields that are commonly searched. Say, for example, you have a product table and everybody's searching for color. Everybody wants black and gold. Black and gold. We are Pittsburgh, so everybody wants black and gold. I'd put an index on color if everybody's searching it. Every now and then, people do a search on size. I wouldn't put an index on size because it's not a common search. You'll know what common searches are because you'll have logs and you'll see how people are interacting with both your websites, your tools, and your database. So you'll get a feel for what's commonly searched. You can also build an index on fields that always appear together. These are called a covering index. And again, more on these. And then I often like to put foreign keys in a join, especially if I do a lot of joining. I'm unique on this one. You don't have to do this, but I like putting an index on my foreign keys. All right, do not build an index in every table. You can only have 1,000 of them, which is probably 996 too many. Seriously, you don't need a lot of indexes. I was on a job interview for Chatham University years ago, and the interviewer asked me the question, said, how many indexes in a table? And my response was, I don't know, but way more than you need. The guy loved the answer. It was a fantastic answer. All right, so primary keys will automatically build an index. If you're commonly searching a field, build an index. If you have fields that always appeal together, we'll do an index, and then foreign keys is my suggestion. I'm going to talk about some of these right now. All right, so I'm going to start off with this clustered index. The clustered index is built on the primary key. See what I did there? The table is physically stored on disk in the primary key order. So whenever you save your table or you update your table, it's written onto disk in primary key order, which is why whenever you do a select star from a table and you don't give it a sort option or an order by option, it automatically orders in primary key fashion because it's the way it read it from disk. You can have one clustered index on a table. If you think about it for a second, it makes sense. Since the table is physically stored on disk in the order of the primary key, you can't physically store it on disk twice. So you can have one clustered index on a table, and that clustered index will always be on your primary key. And again, you don't have to do anything about it. SQL Server will build it for you. If you don't want to use SQL servers, you can drop that index and rebuild it, but it's a lot of work. I just leave it alone. Another type of index is unique index. Now I put a picture of DNA here because DNA is of course unique to each and every one of us. You can set up a column that must contain unique information or does not have repetitions. That can be handled by an index. Now that is a really simple solution to a common programming problem of, allow people to add to a list but don't allow repetitions. If you've written that code, you know that's a search through the list. If it's there, don't let them add it. If it's not there, add it. Here, it's just the index. And if you try to add an element to a column in a unique index and that element repeats, SQL Server will say nope, and it won't go in there. You often find these on candidate keys or alternate keys, whenever you have more than one key that could be primary in a database. A non-clustered index is your normal index. This is on some non-primary key and it's used to speed searches on that field. Now, this is a picture of a card catalog. Everybody listening to me probably doesn't remember what a card catalog was, but what we used it for was to find books at a library. I remember going down to the Carnegie Library down in the west end of Pittsburgh, and it had approximately 10,000 books, give or take a few. Now, let's suppose I was looking for a book on astronomy. I could just walk through the stacks and find a book, or I could go to the card catalog, search for the topic of astronomy, and it will tell me what books it had in the library and where to find them. That's a non-clustered index. It made it quicker to find the book. You've heard this phrase index in your life. If you pick up your database book and I ask you to look everywhere in the book for the word table, you could start on page 1 and read every word and write down the page numbers for every time the word table is mentioned, or you could turn to the index, the back of the book, and it's already done for you. And it speeds up searches on that field, speeds up searches for that word. Since you can have 1,000 indexes in a table and you have one clustered index, you can have 999 non-clustered indexes. A unique field would be another example of a non-clustered index. Fourth type I'm going to talk about, and there are several more you can look up in the Microsoft SQL Server documentation about indexes, things like heap index. I'm not worried about those. But the last one I'm going to talk about is called a covering index. Now I use a bunch of grapes here because people typically don't just eat one grape. You grab a handful of grapes, you grab a bunch of grapes. Likewise, there's often data that's always together. Think about address. If I want to send somebody a letter, I need address, city, state, zip. It's always together. If I'm building a database that's doing a lot of mailing or creating bills and I need address, city, state, zip all the time, I can build an index in that, or called a covering index. The covering index, when it writes the disk, those nodes I showed you before, the A's, the B's, and the J's, etc., will have the address, city, state, zip of every record written on disk. Now, that does eat up some more disk space, and now you have duplication of data, but SQL Server manages that. So you don't have to worry about you updating one place and then it not being updated somewhere else. All right, so a covering index, more than one field. I don't use these a lot. Typically, again, if I find a scenario where my users and my programmers are always using a grouping of fields, it makes sense to build a covering index because then you'll read quicker. Okay, so you got the basic theory of index. Let's create them. Now, this syntax is really simple. You've already learned in SQL Server there's only so many verbs. We've learned the create table. We've learned create database. Guess what? It's, drumroll please, create index. Surprise! Create index, give it a name. On your table, parentheses, fields you want an index on. You only need fields if you're building a covering index. If you're building a standard non-clustered or a unique index, just one field there. All right, so let's build some. I'm going to switch over to SQL Server. Again, I'm going to use Henry Books. Again, the Henry Books is from Philip Pratt's excellent A Guide to SQL book. It's a simple little table. For the purists out there, none of these tables from Henry Books need an index. There's only 20 or 30 records in there. You're not saving anything. But if you have databases like AdventureWorks or Wide World Importers that have 20 or 30,000 records per table, an index makes sense. All right, so I'm looking at my author table here. And I got my book table here. See that each one of these guys has an index, and it's called PK, name of the table, and then vomit. The vomit was given to you by SQL Server. And as you pull over a little bit, you see it's a clustered index. Likewise, PK, book, vomit, clustered index. The vomit may be different on your machine. It's just a unique number that SQL Server came up with. I want to create an index on last name. Create index IDX last name on author last. That's tough, isn't it? Bam. If I refresh over here, find refresh, there it is. Look at that, there it is. Now I named my index IDX last name. IDX, of course, is index. This is the official Microsoft SQL Server suggestion, is to start them IDX underscore. Name them how you want. If I want to build a covering index, can't find the home row keys. Oops. There we go. Again, a refresh over here. There it is. Now, I probably have way too many indexes in this author table. But you see, this isn't a challenge. All right, so I've created a couple indexes. I've introduced some problems that I now need to fix. And I'll talk about those problems for a minute. But let's suppose you want to see all the indexes in our table and not have to do it in the GUI world. Run this store procedure built into SQL Server. SP is store procedure. Help index is a help index procedure, and it's on the table. And I see I've got my indexes I built, IDX full name, non-clustered. On primary means the primary storage where it's located. And then here are the keys inside of it. IDX last name, non-clustered, author last. All right, so the Let me go back to my notes. As I said, I introduced some problems. I'm going to define these problems here in a moment. Here is the syntax if you wish to. Why aren't you going forward? All right, there we go. So SP help index, table name, shows your indices on tables, or you could do it in the GUI, whichever you prefer. Let's now talk about the problems I created. Recall that I built a B tree. By default, SQL Server is going to make that index as efficient as possible in terms of disk space. It's going to use as little disk space as it needs to, which means adding nodes can be a problem. Now, I'm going to make the assumption here that each one of these nodes can have up to 3 elements in a node. Now, I'm just making that assumption. I don't know for sure if that's how I set it up, but let's just go with it. Okay, so if I want to add the letter I, it's not a problem. I can't add it here because there's no room at the end, but I can add it here. So I could have I, J in that root node. That's okay. I would be before J. As long as I is less than J, we're okay. Likewise, I could add N. I can put N right here. I can't add G. Think about that. I cannot insert into table G. The problem is my index. There's no room to write it here. This is a 3-element node. G would fit here. In order for me to do this, I'd have to start moving things around. SQL Server will not automatically move stuff well. It'll move stuff, but it won't be efficient. It might start throwing additional tables on. Like it might split this into 2 nodes and move one before D. You're not entirely sure what it'll do, but the end result will not be great. If you're building tables that are rarely updated, you don't care. Example, the states of the United States of America. There's 50 of them. There's been 50 of them for longer than I've been around. Every couple of years someone talks about let's add Puerto Rico, but it never happens. So if you don't have any room to add elements in your state table, that's okay. But your customer table, you want to add new customers every day. And when an index gets screwed up, you now lose the benefit of the index because the screwed up records slow down the searching. So let's talk about how to fill this. All right, so fill factor here. Fill factor is the percentage that describes how much room to leave in nodes. The default for this is 0, which means there's no room in the nodes. There's fill as possible. You want to leave more space in tables that grow or shrink often, like a sales table or a customer table. I'm not even sure if you'd have an index on a sales table, but just go with it. You definitely have one on a customer table and on a product table. You definitely have some indexes there. So you want to leave some space in those nodes. That way, when new customers come in, you don't have to worry about shuffling all your records around. You just throw it in the extra node. So back on that example I gave you, instead of setting that max to 3, set it max to 7 or 10. Give some room for it to grow. In the real world, I dealt with this once when I worked at a law firm many years ago. At this law firm, I was a database administrator. I was also a debt collector. I wrote letters. I called debtors. I stocked the shelves. I was your basic lowest level on the pay scale employee. I did everything. My boss, Mr. Apple, at one point asked me to organize the shelves, and I did. I organized the shelves beautifully. He came over and said, "We're getting new toilet paper tomorrow. You didn't leave any room for the toilet paper." That's what's happening here. If I get a default of 0, when we get new toilet paper, I have to rebuild the shelves. So I got smart. The next time he asked me to rebuild the shelves, I left space after everything, so that when new stock products came in, I had room to throw in the space. That's what fill factor is. It's given space at the end. All right, so here's an example. Let's create some index blah on table field. Now, here's how you put in these properties. You say width fill factor equal 80. What I'm doing here is I'm leaving 80% free. I'm filling my nodes 20%. So this gives me room to grow. If, again, your tables grow a lot, this is something to deal with. Another problem that we introduced, but is a little behind the scenes, something called statistics. This is not the boring math class you hope you might have taken in high school. This is something even weirder. Um, Behind the scenes, SQL Server maintains a histogram of information about records in the index. Think histogram like a bunch of bar charts grouped together. And what the bar charts are indicating are the number of items in 20 bins. And a bins is a range of values. Simplistically, let's suppose you have the numbers 0 through 100 in your table and you build an index on that column. You want to know how many zeros the 10 you want, etc. What SQL Server will do is it'll look at all of those numbers, 0 to 100, and it'll create 20 sized bins, roughly equal. So it'll be like 0 to 5, 6 to 10, 10 to 15, etc. And it will have in there the number of elements that are between 0 and 5, 6 to 10, 11 to 15, etc. That's the histogram. You don't need to look at it. You really don't need to deal with it. You can look at it if you want with an SPC command, but it's really not a big deal. But you have to understand it's there. SQL Server will use this histogram whenever it does its query optimization. Again, something not to worry about today, but you got to know about it as you're building indexes. By default, SQL Server will not update this histogram. If it's a state field, nobody cares. It hasn't updated in 20 years. But if it's a customer, that column will change often. So you have to learn how to update the histogram. When you set statistics no recompute equal on into your query, it'll tell SQL Server to continuously update this histogram. So as you add records, it'll rewrite the histogram, meaning your queries will optimize themselves better. If you don't remember this, and you never use these, you can periodically run the next command. Alter index, whatever, on table rebuild. This will rewrite all your indices, so if your nodes have gotten weirdly populated, this will re-optimize them again. This will rebuild your histograms. This doesn't take very long to do, but it's not something you want to run in the middle of the day. You want to run this when people aren't on your database. Microsoft SQL Server includes a really cool tool called the SQL Server Agent, and the agent is how you schedule tools. And that's the command, alter index, whatever, on table rebuilds. Okay, so you know how to build indexes now. You know when to build indexes, which is only on stuff you search a lot on. You learn about a bunch of different types of indexes, including clustered index, non-clustered index, unique index, and a covering index. And you learn two of the important properties of indexes, which were fillfactor and statistical recomputes. All right, you should be good now to build any index or build any assignment you need in index. Thanks. You have a good day.